Report to this computer. All right.
Hey, do you want me to do the intro or you?
I guess I can do it. Hi guys. I don't know if we have any repeat viewers, but me and Nathan are tutors at the FSC Tutoring Center. We were also former BOSI 340 TAs. And we're going to be covering the last two units of your guys. We'll present the last two units uh, for your guys' final kind of review them because they will probably be the most prominent units. And then afterwards, we can cover specific concepts from previous units or specific questions on any unit. But we have covered some of the earlier concepts more thoroughly in our midterm review, which we have like a recording. If you guys are all from Paraputi, we have a recording that's like 2 hours that covers a lot of this. So we will probably not focus too much on them unless there's specific questions.
Okay, this is me. So we're gonna start with lambda calculus, everyone's favorite subject in 340. Go ahead. So I'm not gonna focus too much on this, but this is the syntax and grammar. Hopefully, you should be familiar with this. The more important thing, like, is that the grammar is ambiguous. It's ambiguous. So how you derive a certain input. You can have different derivations for it, like the same input. So obviously this leads to our disambiguation rules, which will be on the next slide. Yes, so an abstraction, which is a lambda x, like actually I can write, I forgot. So an abstraction extends as far right as possible without enclosing right parentheses. This is also important for binding, but we're going to focus on the disambiguation rules first. So when you see lambda x, okay, it goes as far right as possible until it reaches either the end or an enclosing right parentheses, like here, here. So this is important when noting for when you apply the disambiguation rule, specifically when you're drawing parentheses around a lambda expression. You basically want to do draw parentheses around, for example, x, y. You always want to draw it around, encompass it in a parentheses. More so just when you're applying the other disambiguation rules, you don't accidentally cut it off, right? If you drew these parentheses, if you had this expression, for example, and you're doing, the next one, application, right? And you're like, okay, what if I draw here? Then this wouldn't work because by drawing parentheses around this, you're cutting off this y. So this y is no, I mean, if this was an x, I suppose this, like, for example, x is no longer bound to that lambda x based on how you draw parentheses. So these disambiguation rules, specifically the body of abstraction, is very important. Now, I'll go into another example in the next slide on how to apply it. So, yeah. So the next rule, disambiguation rule, is application. And I kind of want everyone to think about it as applying basically leftmost pairs that don't break body of abstraction. The best way to summarize it is that you ensure the ensuring that the best way to summarize abstraction, I suppose, is ensuring that variables remain bounded to lambda x. Uh, and then after you apply those parentheses around the abstraction, then you can do application, which is basically maintaining left associativity in this specific pattern. So, for example, here's this lambda like long input right here. Uh, what I do first is apply body of abstraction, basically drawing parentheses around each lambda abstraction scope. So, I mean, for example, this lambda x right here, its scope goes all the way to the end because there's no enclosing right parentheses, which is why we get like right here and here. And then this lambda x, for example, goes all the way to the end as well. So we get this right there. This one's already enclosed in parentheses, so we don't need to draw anything there right now. This lambda x also goes to the end, so which is why we have this. And this lambda x also goes to the end. So that's pretty simple compared to application. So application should be done after you apply those body of abstractions. Uh, they should be seen as leftmost pairs that do not break body of abstraction. So basically, if you, I'll give an example right here. I think I used the same example on the previous slide, but lambda x, and we just do x, y, and then z, right? The first thing you would do in this situation is just apply body of abstraction, which is, I call it enclosing the scope because that's the easiest way of seeing it, in my opinion. So body of abstraction, just draw parentheses around the scope, and then application. It's left. Remember, it's leftmost pairs without breaking body of abstraction. So, for example, use a different color. This is no good because you're cutting off, like, this stuff is no longer bound to this lambda x, right? So you're basically cutting it off. That's not good. So you remember it's leftmost pairs without breaking body abstraction. So you look at the next left pair you can do, x, y, that's fine. And then remember, it's pairs of t's. So this, remember, if you looked at the grammar, this is I guess I should focus on this. Yeah, right there. Uh, that t can leads to a t. So this is a t. This is a t, and an x is x, y are also t's. So this is a t. This z is also technically a t. So you can draw parentheses around that. So this is one part of the pair. This can be another part of the pair. So you draw this around a pair, and then you look at. I mean, this parenthesis also makes it a term. So the reason why you want to draw parentheses around this is because it's used for finding the redexes, which is very important for uh, applying beta reductions and just using lambda calculus in general. Uh, the next slide will also have another example I'll go over. So actually, no, I guess not. I think it's on a later slide where I do that. Do I? Let me double check. No, I think I do. I do something later. Yeah. It's after redexes though, for some reason. So, okay, yeah, never mind. Well, I'll go over a more in-depth example later. Yeah, bindings basically. Did I write that blue? Oh, that's your line. That's why. Never mind. Sorry. Is that your line? Yeah.
That's your line,
Yes,
big man.
it is. Oh, yeah, it is. It is my
That's
line.
embarrassing, buddy.
Hey, shush. Uh, yeah. So next we're gonna go into bindings, right? X is bound to lambda x if x is in its body of abstraction, which we talked about earlier, and lambda x is the closest lambda x to the left of x. So it's the nearest. It's basically has priority. Uh, x is free if it's not bound, and y cannot be bound to lambda x. This should be pretty simple. So next slide. Okay, redexes. This is probably the part where people start having a lot of issues, but it's pretty simple once you learn actually how to, apply those two disambiguation rules, because we use those disambiguation rules, specifically the parentheses, to locate these redexes. It makes it so much easier. So it should be noted, a redex has the form of lambda x t t prime, where t and t prime are terms. It should be noted that it has to be in this form. Something that is not acceptable is, for example, x, lambda x, x, and x. This would not be, there is no redex here because technically, if you applied the disambiguation rule, specifically application, you would first apply parentheses here, right? Leftmost pair without breaking body abstraction in here. So this is not a redex because this x would have to be a part of this lambda xt in order for it to be a redex. So this would be like the lambda xt and this is t prime, which is not possible because this is just x. So it should be noted that if you see something of this and there's two right parentheses here before the t prime, then it's probably not a redex. It's something I want to note because a lot of students get tricked up on that. Let's see. Let me get rid of that. Yeah. So yeah, identify these redexes though, you should definitely apply uh the disambiguation rules, body of abstraction right here, and left associativity, which I take from the previous slides. Yeah, and a reducible expression is a term. So this means that you should be able to put parentheses around a reducible expression, which kind of goes back to what I said earlier, right? That you should be able to basically you should be able to drop parentheses around this and it would be valid. So next slide. Yeah. Yeah. So here's kind of example where I do both the disambiguation rules and use those disambiguation rules to find redexes. So here's our first input, body abstraction. There's only one really need to worry about. It's this lambda y, just drop parentheses around it. Next is application. That's the trickier part. I'll probably go in step by step here. So when looking at this, it doesn't really, I mean, you don't, it doesn't really matter too much where you start. You just have to make sure the rules do apply. So for example, I could start here, right? You cannot do this, right? Because then this X is not bound. So you move one to the right, and then you see, okay, I can draw parentheses around there. Look here, I see another one right here. Just draw parentheses around here. And then this lambda, you can definitely make pairs here, right? So make here, 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 here. This red already exists, so it already encompasses this and this. So that's a pair. Then you could do one final one around here. And as you can see, that matches kind of what we did for application. And that does match. So that's applying application right there. And then from that, we can identify reducible expressions, right? So right here, this is remember, it's lambda x t, and then it's t prime, right? That is the form. And this t can be this, for example, right here, that's lambda x, right? And then this is obviously the t. And then once again, this is t prime. Remember what I said, this can be a term. So this blue right here makes this a term. So you can encompass this like in a term. So that's the idea. But yeah, so there's one right there. Uh, Another one you can identify is right here as well. Let me kind of clean this up. So I'll go over that one. First thing you notice, right? This red makes it so this entire thing is a single term. So you look within that term, you see this lambda x right here. And then this xx can be the t. It's already enclosed in parentheses. And then this whole thing can be a t prime. So that's another redex right there. And okay, I think we're ready to move on. By the way, at the end of the lambda calculus slides, I'll go into a much more complicated one. One from one of the Bosnia homeworks, but I go way more in depth on how it works. So hopefully that'll also clear things up. Uh, I think you can get rid of this slide. Honestly, can you skip? I think I took this from the content training, and I'm gonna skip that because that kind of was the activity. So, whoops. I'm just gonna delete that right now. I think I just forgot to delete that. There you go. Okay, beta reductions. So this is where things get interesting. You can read it as replacing the x's and t that are bound to lambda x, right? So this is t, all the x's in here, plus lambda x, you replace it with t prime. Yeah, you can also think of it as applying the function to an argument. This is kind of the thing with functional languages. So the function is lambda xt and the argument is t prime, which is what we did with redexes, if you saw that. So for example, given a function lambda x ax bx ax, you can read it as the function of x that evaluates to ax bx ax, and given an argument v, you just replace the x's with v, which is, think of like arithmetic or functions in math, right? That's kind of what we do there, just replacing the argument, replacing with the arguments. So I mean, took this from the slide. Right here, sorry, the zoom bar just like pops up out of nowhere sometimes, so it covers the bottom half. Let's see, yeah. So right here, you have a redex. This itself is a redex, right? This is the lambda x. This is the t, and this thing can be the t prime. Yeah, it also mentions there, I suppose. And then then you can beta reduce it. So you basically replace you get rid of the x, lambda x, right? And then you replace all instances of the x with lambda yz. So that's how you get lambda yz and then y at the end. So this one becomes like lambda y dot z, right? And then y. So that's how you get that. And then you can further reduce it. This is kind of what currying is, which we'll go over later. You can basically kind of nest lambda expressions in there, and you can this is also redex. You can also beta reduce it, and then you get the final value, which is z. No more redexes, so you're done. But there's also an issue with basically scopes being possibly bindings being changed, because this might share might share a similar lambda here. So bindings could be affected by replacing the like some free things can become bound. Like this if this argument was free, for example, actually, just go to the next slide. I talk about on the next slide. It's just gonna be so much easier. Yeah. So if by doing a beta reduction, basically, if a bound slash free variable obtains a new binding, you must do renaming, and this is pretty simple. Uh, okay, I guess I should get an example of uh basically what would entail if we don't rename. So if we had this expression right here and we didn't rename it, we would get this. And the issue with that basically is this z, which was this z is free. I'm writing with the mouse, so please forgive me. So this z is free right here. We then and I should note I believe this is the redex right here. So this is the t prime. So you're applying the z to all instances of y in this lambda in this t, right? So this y would become z. But then so this free is now bound to this one when it was I can use text originally free. There we go. Yeah. So yeah, this Z was originally free, but now due to the fact that we didn't alpha rename, this Z is bound to this lambda Z, which is not what we want. So we must do alpha renaming when in the situation. So I mean, and it's pretty simple. You just basically change the lambda Z that like you change the lambda fraction that would change the binding. So this lambda Z now you just change it to lambda W. You replace everything that's bound to this lambda Z with W as well. That's important. And basically, the thing is, now this keeps it binding, still bound. Like this is still bound to the same lambda abstraction, right? That's important. We want W to stay bound to this lambda W, which is originally Z bound to lambda Z, right? But now we can also now the Z is now free, right? It's free, still free. So we're maintaining the bindings. That's the important thing. So with alpha rename, we're retaining the bindings, the original bindings or lack thereof. In this case, with Z. So that's pretty simple. Lambda rename. You can name it to anything. It could be A, or it's just yeah. So that's the main thing. Just rename it. Uh, Next slide. I think I go over kind of a combination here. Yeah, so this is just a little short example when I cooked up. So you have the redux here, right? Yeah, sorry. Okay. Yeah, so you have a redux here. You notice right here that there's this Z is bound to this lambda Z, so that's fine. That will maintain its binding, but this Y is free. So if you were not to do alpha renaming, this y would become bound to like because right now we're like this is a lambda x, so this lambda x would be a I don't have the I'll just do L. I'll just use LZ dot YZ, right? So this x would replace with lambda z yz, which is the t prime, which would affect its binding. So this y would now this lambda y would affect this y would be bound to this lambda y if we did beta reduction. So it'd be free and then not free, which is not what we want. Not what we want. So what we do is we rename. What we basically rename is just this lambda y to I choose you, and then everything this y also becomes u as well. So we just change the name, and then this is the answer, right? So all the bindings stay the same. And also, I should note we don't have to change z, right? Because this z is still bound to this lambda z after we do the reduce, after we beta reduce, right? This z is still bound to this lambda z. So we don't need to rename this lambda z. It's fine. You only need to rename if it changes bindings after you do beta reductions. So uh, next, yes, currying. This is kind of goes into the I think the previous example we showed with beta reductions or something. Basically, you can convert multi-argument functions into a chain of single function argument functions, which is important for different churches Church's booleans. I forgot the name, but like different functions. For example, true, false, which you should be familiar with in your homework, I believe. Like the true, false functions, first, second pair. They're all just basically abstractions of just like basically I don't know how to describe it. Curried abstractions. So it's just like a bunch of chain of single arguments. I'll go into an example later. Actually, right now, I'm going to an example right now. So this is the true function, right? What true does, it returns the first of two things, which is pretty simple, but the actual how it actually works is it's basically curried reductions, right? So let's say we apply this to x and y, right? We like if you did like originally you just see like true like if you didn't know how this worked before, it would be like true x y. You'd be like, oh, it true just returns the first thing, so it's just x. Yes, you're right, but it works because it's a lambda extraction, right? It's an abstraction. It's like true hides what it actually does. It's just a placeholder. So we kind of so here I replace true with lambda a b a, which is the lambda expression. And how it works is that you get the first redex. There's only one redex right now, which is lambda a, which is the lambda function. This is the t. The x is the t prime. Uh, then you just beta reduce it, right? So you apply this x to this a, which gives you lambda b x y, right? You get rid of this lambda a, you replace this a with an x, and then you have the y still. You clean up the parentheses a little bit, and then you get this final beta reduction, right? You get lambda b. This is your t prime. But you note, I guess I added the t prime there as well. But note that there's no y in this t. So in this case, you don't you try to add it, you can't add it, so it's vamooshed, right? So you get rid of lambda b, you get rid of the y, and then you end up with x. So that's how you get the first of two things when you use true. That's actually how it works in the back end. So that's example of currying right there, which is pretty cool. So if you're given basically an input with multiple redexes, then they're we're given two ways of figuring out determining the order of which one we do. Basically, we choose which one we choose to do first. Both are valid. Both will end up with the same result. I will give you an example at the end where you kind of touch on it a little bit. Uh, but both are valid ways of reducing in a lambda expression. The first one, normal order evaluation. You look at the leftmost outermost redex, which is pretty simple. So the leftmost outermost. Call by value is a little more tricky. You do the you reduce the one who's amongst read it. I guess. Can you move on to the next? I totally forgot the call by value real quick. Can you just go one more slide as well? Yeah, yeah. So let me double check. Yeah. Uh, yeah. So is it the first one you? I totally forgot. It's not. I think I put the right mode. What did I put? Oh, let me double check because I swear it was something else for some reason. Call by value. Uh, yeah. Okay. So yeah. So call by value is basically no reductions can be done inside abstractions. And a redex cannot be reduced unless its right hand side is a value. So yeah, I totally forgot about that. Yeah. So you can't do one because this is inside this lambda x abstraction, right? So that's the first rule. The second rule is that a redex cannot be reduced unless its right hand side is a value. So this eliminates three because this is not a value. That's what call by value is basically saying. So it's you can't choose a redex if it's within an abstraction and or if its right hand side is a value. You choose the first one that is not. So I think the leftmost one that is not. So or anyone that is not. So which is why we choose two, because this is not inside it, not inside abstraction. Why am I writing with the pen? Not inside an abstraction, and that's a value, right? All right, let's go back to normal order. Just one more slide. There we go. Yeah, so normal order is pretty simple. Like I said before, you look at the right, you look at this and you see the basically the leftmost outermost. Lambda x is this three is leftmost outermost. That's pretty self-explanatory in my opinion. So leftmost outermost. That's normal order up. normal order evaluation, then you reduce this lambda x right here first. Okay, we can probably go on to next after call by value. Oh, Church's numerals. Yeah, so Church's numerals are kind of are how natural numbers are represented in lambda calculus. Once again, it's an abstraction. So, for example, if we're given 4ab, it's not like it's of this form, right? But how it actually works is, right, you replace this 4 with the abstraction, right? This is just 4 is just an abstraction. This is actually what's in the back end. You apply a to all these s's, which gives you lambda z, a z. Then you apply b to lambda z, which is gives you this. So that's what you get there, right? I'll go over that in the next slide a lot more because now we have our final lambda calculus example. This is taken from one of the Bozzi homeworks, but I think I go into a lot more depth on each step by step, and un, I kind of show the back end, little what's the under the hood stuff as well. So first things first, look at this. I then apply, just some parentheses, as you should, which gives you 2, 2, AB. I'll just go ahead and say it. The first 2 is the first one I'm going to mess around with because this will be because this is remember this is like this the 2 itself kind of represents the lambda xt, right? And then this 2 would be the t prime, right? Let me quickly move to the side, right? So 2 itself represents the this is the lambda xt, right? Because it's under the hood right here. This is the lambda xt, and then this 2 is just the t prime and encompassed in parentheses. So you can't start with this 2 obviously because then I mentioned before this 2 is kind of stuck with this 2 right here. So we have to start with this one. This is our redex right here. So we start there. I conveniently replace the 2 with the lambda expression associated with it. So this right here is basically what 2 represents. So first things first, we, beta reduce it, replace the S is in here with 2, and then conveniently, once we clean up the parentheses, this then becomes another redex where this is the T prime now, and this is the T, because the way we reduce it, we get rid of this, get rid of this. Now this one will be part of this A. So then we beta reduce with the A, and then that's how we get 2A, and then B. And then we have another reduction we can do, right? We can do right here, this 2 right here. We can do this 2. And this, you could also, I guess you could technically do this 2 as well, but actually, no, you can't. It wouldn't be clean, I think. So yeah, you start with this 2. You do the same thing as I did before, right? You replace this 2 with the actual lambda abstraction. This 2A becomes this 2A is the T prime. This is the lambda T, the lambda T, right? The lambda T. And then you beta reduce it twice. Remember currying. This is a curried function, right? So you apply the 2A first, clean it up. Then you see the B is the next. This is another redex right here. So you apply that. You end up with 2A, and B. And you should notice there are technically 2 redexes we could do here, right? We could do this 2A. This is the right there. We could start. It's kind of difficult because it's curried, but this would be valid. We could start here. We could start with this 2A right here, or we could start with this one. This kind of goes back to how we did normal order and call by value, which next slide, please. Let me clean this up as well. So this kind of demonstrates the idea between normal order and call by value, right? Normal order evaluation, it's leftmost, outermost, which in this case, this 2A is the leftmost, outermost. But we could also do call by value first, which is, once again, it's just basically one that's not its right-hand side is a value, right? A is a value, and it's not within a lambda expression. So you could do this 2A as well. So we go down both paths right here. So if we did the normal order way, if we choose this 2A first, we I guess it does look kind of messy, which is why we have the abstractions in the first place, but I kind of want to show the under the hood. So we replace this 2 with the lambda abstraction. We apply the beta reduction A's to here. We curry, it's a curried function again, once I said. So this 2AB becomes is also a T prime after we apply the first beta reduction. We apply this, we get this. We see this redex right here. Do the same thing. uh, A right here is apply A first, then B is next, and then we end up with 4AB essentially. And then call by value, we start on the right-hand side. We do similar process, right? We do A right here, then B, which ends up with 2A, AAB, which is different from here, obviously. But once we do the final redex, we notice that it ends up being the same. So yeah, that's basically it for lambda calculus. It's definitely probably one of the harder concepts you'll need to learn in 340. So I guess I should ask any questions before we move on to the next portion, which is like the runtime environment stuff. Any questions on lambda calculus in general?
The only thing I'll add is that this does, or kind of the primary theory that Nathan was mentioning, is that lambda calculus essentially it doesn't matter which order you reduce things if it's reducible and you just follow the path. Um, all orders will result in the same answer, but there is a key exception. I don't know that you'd ever be tested on this. If for some reason, let's say we're doing normal order and we get something like lambda x, x, something like this, which creates an infinite loop. I think that's it. Yeah.
Yeah, it's an
If we
infinite
get
loop.
an infinite loop, we cannot say that call by value will also get an infinite loop. That's the only situation where it's possible that the answers are different, is if one path leads in an infinite loop. We cannot say all paths are infinite loops.
You know what?
But
Actually, I
otherwise,
think one of the previous Bozzy homeworks actually had this situation. So yeah, you're right. Oh yeah, keep that in mind. Keep that in mind. Technically, yeah, this could result in infinite loop, which might obviously won't be equal. But now on to Thomas.
all right. So first thing when we're talking about runtime environments is understanding variables. Variables, you guys have used them throughout your entire time programming. They're kind of taken for granted, but it's the computer doesn't really understand variables in the same way that we do. Variables are a compiler or a language thing that helps us organize our ideas better and our data, but the computer has no concept of variables. It has only the idea of memory and placing things into memory. And so as a result, if we think of data as these variables and the computer thinks of data as these memories and or this memory and we want them to be separate still, we need a kind of transition step where at some point we take all of these spots and we transition them into real pieces of memory so that we replace all instances of A with the usage of that memory. And then once we have that, we can start just manually putting in those actual memory. I think that's a value. But like for example, later we determined that we want A to be at this memory address. And so a symbol table helps us transition from our rough idea of just variables being a concept that we use to organize data to the actual memory implementation of it. And so that's pretty easy with global variables. The compiler knows how much space it's allowed to take, and it just increments every time. I think on your projects you've done this. You literally just check the variables, see what type they declare it as, and okay, that's the amount of space. I'm going to hard code that address, or not hard code. I hard determine that address and just replace all instances of A with that address that we determined. But that is a little bit of a problem when we think about local variables because local variables are local to functions. And we don't know what the situation is like when we call the function. If I call main, maybe I can assume, hey, main is the only kind of block that we will be looking at. If main has variables A, B, C, maybe I can say A will be at 0, B will be at 1, C will be at 2. But what if main calls itself recursively? A, B, C. Well, I can't say that A will be at 0, B will be at 1, and C will be at 2 because these are two different variables. And so that would mean if I change the variable in the recursive call, it would change it in the parent call. And that's not a great idea. So we kind of have to store our local variables somewhere and kind of keep incrementing that space to keep them separately. So when it comes to local variable, it's primarily done through the stack, which I'm sure you guys are at least tangentially familiar with. Um, each variable declaration can be thought of as a request for more memory from the stack. So we're used to situations where we're calling for memory from the heap using malloc, and this is very explicit. But when we do something like this, in a very similar way, we are saying, hey, I need memory for this variable. So this is actually also a request for memory. And in kind of the previous, I don't know if, well, in the box kind of circle diagram, both of these create a box. Um, but there's a little bit of a problem. Like we were talking about before, how do we determine where something is, or where a variable is? Because if I call this function foo, I have no idea how many functions called it before. And so I don't know how far down the stack we are or how far up the stack we are. So we still can't hard code our addresses. Further, let's say I'm done with foo and I want to give that memory back. How do I know how far to free on the stack? That's a separate problem because, well, I don't have any idea how much memory my thing used. I just know I incremented it every time I needed it. Um, and so we need to deal with this problem using something called function frames. We add a new register where we talk about the beginning of the frame. And that helps us solve a lot of issues because, well, we ask for memory from the stack. So the top of the stack is just going to be the top of the function frame. We don't need a new register for that. But the base is really useful because it helps us, first of all, it gives us constant offsets for our variables. So we don't need to hard code the address like we did before. Based on the function declaration, I know how far from the base these variables should be placed. So now we're back to things, values we can kind of, in a sense, know at compile time. We can know, hey, C, I don't know where C will be in actual memory. I just know it'll be a certain amount from the base. And so that helps us organize things. It helps us keep local variables. It helps us keep different function frames separate. They don't need to know how far up on the stack they are. They just need a base pointer to build their variables from. Um, and so when we look at this example from your guys' notes, we see, hey, when we are setting up the function frame, we move this ESP or this EBP into, I think I have it backwards. I always forget the order because this is Intel syntax. Um, so this is, yeah, this is moving the stack pointer into the base pointer because if you think about it, if this is our function that we're calling from, so something like this, and we want to add another function frame, it'll look something like this, RBP2, RBSP2. And so we can note that the end of the previous frame is the start of the new one. And so that's what we're doing with this step. And this subtraction is allocating space for our variables. It's allocating 16 bytes, I believe. Um, then we are moving 10 into the variable spot for A. It's at a constant offset. And yeah, so the important part here is just how we're setting up the frame by moving the RSP, or the top of the frame of the previous one, as the base pointer of the next one. Notice, however, that I said this is incomplete. So when we're looking at a function, we've got several other things to consider. Where do the arguments come from? It would be kind of difficult to basically say, hey, if I have x and I call f of x, it'd be difficult to tell x, hey, when I gave you this value, I actually was talking about this one up here, although there is a way to do that that we'll discuss. But usually what we do is we copy the value entirely onto the stack. So when we're setting up our new function, this is our old, we copy values for the arguments. So that's why, or that's an example of pass by value, where if we change the value inside the function, all we're changing is this copy we made. We aren't actually changing the value on the outside, or the value we passed. Um, but this does bring up a different question. Before in the function frame, we were just using it to keep track of local variables. But is that all we need? So we already discussed we're keeping track of the local variables. That's the entire point of a function frame. And we also need to copy the parameters. That kind of makes sense because if we have something like foo, A, B, C, these are almost, you can consider them just local variables of the function foo. So we need to copy the values into those local variables. But then we need to think, okay, what if we call the function within a function? How do we go back? Because from this perspective, this is our RBP, this is our RSP. It's fairly easy to reset the RSP because the beginning of our function frame is the end of the previous frame. Okay, that's pretty easy. Oh, whoops. Well, but how do we go backwards with the RBP? Because we don't know how big the previous function frame was. Also, if I'm in this function, how do I know where to return? Um, in some implementations, there might be, like I know RISC-V has a return address register where you can restore the return address. But what if there's a third function? We only have one register. Um, so we need to think about how we keep track of where we're going back to. And then also we have temporary variables potentially, but I don't think we really discussed that here. And to figure this out, we essentially store those values onto the function frame. We add the return address, we add the previous function's RBP into the function frame, and that just lets us go backwards. But who stores that? Like, there's two perspectives we can think of, the caller and the callee, and each perspective has access to different information. So, for example, the callee, if I make the jump, I change my PC to the next function. Well, I didn't store the return address anywhere, let's say. I have no idea where I came from. The computer doesn't keep track of, okay, what's the last instruction we did? What's the last instruction we did? All the computer cares about is its current instruction and maybe, depending on how things are laid out, its next instruction. It has no way of tracking the previous instruction. And so if this is our caller and this is our callee, we need to save the return address in the caller because only the caller knows, hey, this is where I want you to return to. Return to me. And then we have this. Can the caller ask for local variable space? This might be possible if you do some interesting stuff, but for the most part, if we kind of think of them as separate responsibilities, the caller really shouldn't have any idea of how many local variables the callee has. The callee should be the one to take care of that. It's the callee's variables. Why should the caller know about them? And so we realistically can't set up the local variables until we are after we have made the jump to the function. Now, those are two distinct cases, but there's some things that can be done by both parties. The callee can allocate space for the return value. If I have int foo and it returns an int, both the caller and the callee know what it returns. The caller knows because it needs to know. It needs to know, hey, when I call this function, I want this thing back. The callee, on the other hand, also knows because it knows what it returns. And so we need, and potentially both sides could say, hey, put 4 bytes on the stack for the return value. So there's some ambiguity there. And the way that it's kind of organized is system dependent. And so in this example, we'll be using the XV or x86 calling convention, specifically this one. x86 has other calling conventions. I believe System 5 is another one. And that one puts a lot more into registers and stuff. But this one is pretty simple, and I'm pretty sure he just wants you to roll with this one. All the caller does is it says, hey, here's the arguments. That the caller has to do that because it's the only one that knows what values the arguments are. So it has to copy the arguments. And it also does the, is x86 going to be on the exam? Unlikely. What they might ask you though is this, where they might say, hey, what does the caller need to do? What does the callee need to do? I'm not entirely sure if like how much they're going to go into this type of thing, but I would find it unlikely that they're going to ask you what are the x86 instructions. Push and pop are how you add and take away from the stack, but for the most part, the focus of this would probably be something like this, where we say, hey, the caller needs to, this is stuff that only the caller knows. Whereas here, runtime environment and execution will be on the exam. That's just that's this basically. It's the how we deal with variables and stuff, the runtime environment. And it's runtime because we are setting up the function frames while we are running the program. I don't know if the user gives input, and let's say the user declares how many times a recursive function will recurse. I can't know what the user will give me while I'm compiling. And so it has to be done at runtime. So function frames are a runtime environment. Um, and this is done at execution. So usually that's what they're referring to. Um, but yeah, so the callee needs to put the return. This is stuff that the callee needs to do. Um, yeah, I guess I can do that. This it needs to do, but this either of them could do. So in this example, the callee is just doing it. And this basically is saying the callee, right after the call is made, this is what things look like. We have RBP, that it looks more like a P. But we have RSP, then we make the jump, and things still look like this. So what the caller will do is it'll say, hey, put RBP onto the stack, and then it'll go ahead and change the values. So it'll go, okay, now that's done. I want RBP here, RSP there, and that way we can pull from this to reset to the previous function frame. So this is a more complete example. So note they are, I think there's other specifics, like they want you to put arguments on from right to left. That's just something you might want to memorize. Um, but so like here, you can see they're putting on from right to left. So they're putting on this 10 and this 40. So the 40 comes first and then the 10. But you can see that they're saving the previous function's base pointer. Then they're, so this step, so we have RBP, RSP. What they do, they go, hey, I'm going to save you here. Then I'm going to move stuff around, set up my new function frame. And the frames are pretty consistently sized because when you declared the function, you declare each variable. And so it knows how much it needs for each function. It's static. Um, then it moves the value. And then when it's going back, it pops EBP. So what it does is we have the RBP value, which is currently set to here, and it pops it into the register. So it extracts, I guess it's better. Okay, I'll do it like this. So we have these two function frames. We're going to say the RSP is here, and we have this. So this is the previous function. The construction, this is the saved RBP, and this is the RBP. And so after the transition where we pop and return, the RBP is reset to here, the RSP is set to here, and we use that return address to figure out where to start executing again, right there. Um, leave, I don't think you really need to know this. Leave is shorthand for move. I believe it's move. Dun, dun, dun. It does the kind of, it's a shorthand for these kind of exit steps. Okay. So thus far, we've only talked about pass by value, where we just copy the value. There are a few other ways. Pass by reference essentially binds X to the same memory or the same location. Um, that one is a little harder to set up, and you don't see it in C, but you do see it in C++. Java does this with its objects, where that's why when you change an object inside of a function, um, it changes it on the outside. Pass by name is kind of how C, if you guys have ever used macros or seen them, it literally just replaces the name. And so when we call this function with a of I or an array access at a certain index, all it does is it completely replaces the name. So it's like this function wasn't even called and there wasn't even a frame set up. It just like raw replaces them. There could be some small frame set up, but it's literally using the exact same name. And this can get you in some trouble if, for example, you do increment plus plus I, it just raw replaces it. And so it will, every time that the variable name is used, it's going to call this plus plus I. So if I had X here, it would call the increment operator 4 times. But yeah, so those are the other two. Now this is a little bit if you guys have used some more functional languages like JavaScript and stuff, you might have seen this type of thing, but it's not done in C. Um, in JavaScript, you can kind of functions are treated as almost or the as variables. And so you can have functions inside of functions. I'm not entirely certain if this is possible in C. I don't think. Or if you it is, it's a little bit weird. Um, and in this case, what this lets us do is we have this x that's referring to this parent function. Or sorry, because it's enclosed in foo, it's referring to this same x. And that's kind of interesting because it creates like a function local, global, where like everything outside of foo has no idea what x is, but these two functions have an idea, and you can call a function inside a function. This changes the value, but at no point did we have to make x global. However, this is not possible using our current function frames, because all we have access to is, or the function frames are intentionally made to be completely separate. We know how to go between the parent calling function, but we don't really have any link between these two functions. This x in our current view of function frames is the exact same as, or is completely different than this x. And so this will probably throw an error. And so to fix that, we need another thing in our function frame called an access link, where we essentially, when we're searching for a variable, we have an access link to the enclosing functions. So Baz, in the previous example, was enclosed by bar, and bar was enclosed by foo. And so if we're looking at X for Baz, we check our current scope. If it's not there, we look at the access link, which has the base pointer of the enclosing scope, and we go, okay, is it here? If not, then we go into the topmost enclosing function. If it's here, we know it's there. Otherwise, we stop and we throw an error. These are a little weird, but just kind of know conceptually that it's how we keep track of enclosing a function within a function and having these kind of internally global variables. And then finally, the heap. This is what you do, or the stack has been really nice because it's super easy to allocate and free. It's done for you. Um, However, there are situations, as is the example with heap, where you're not entirely sure how much memory you need, and sometimes you don't want memory on the stack because you don't want it to be automatically freed. And so in this case, we have explicit allocation and deallocation. And so when we're looking at malloc, what even is it? Kind of is the question. We have a system call where we ask for memory from the operating system. The operating system will give us a lump of memory. We'll point to it, give us a pointer, and then that doesn't entirely solve our problem because, well, it's just a lump of memory. And so one way of dealing with it is just ask for the exact amount of memory from the OS, and then when you're done with it, you give it a negative amount using this system call, and you end up freeing it. This is really simple though, and really expensive, um, because you're constantly asking the OS for memory and you're having to switch back and forth. So usually the heap is managed by a piece of software that asks for chunks of memory and then manages which portions are free and which are being used. All right, so that is the kind of presentation completed. So now we can transition on to questions you guys have. And are just to start, are any of you guys from Gordon? If anybody's from Gordon, tell me and I'll send the link in chat. Otherwise, we're gonna post these slides in Parputi's Canvas page. Um, and so you guys will have access to this, but if anybody's from Gordon, let us know now so we can give you access to these slides. But here we have linked all of the other slide sets. Um, so this is modules 1 through 2, which deals with like first follow, regular expressions, um, recursive descent parsing, and then 3 and 4, which deals with pointer semantics, um, box circle diagram, type systems. And so, with that said, we can move on to any specific questions. If you guys have a specific example problem that you can show us, we can work through that potentially. I'll give it a few minutes just to see if anybody can think of something. Is there a recursive dis predictor? Okay, so when it comes to that problem, I guess I'll make a slide just blank.
Yeah, it's the two rules, right? It's the exclusivity of the first and follow sets of two rules.
Yeah, so a predictive recursive descent parser, what they're probably asking you, so first what you need to do is look at the first set of each path. So there's two main rules when it comes to being able to say something is an easy recursive descent parser. The first one is so if S has path 1, path 2, path 3, all of the first sets of these paths need to be disjoint. And that means there can't be any overlap. And that mostly makes sense because if there is overlap, we have no idea how to choose which path to go down. The second thing is that correct me if I'm wrong, Nathan, the first uh, of the S of the has to be disjoint from the follow.
Yes.
Yeah, because otherwise we don't know when we peek, we don't know whether we're looking at the something within S or outside. So these are our two rules. So taking a look at what they're saying there, S only has one path. So it's just the same follow set that they give you. W, why am I? Okay, pretend that's a U. Um, so we have one path, so it just evaluates to that. The follow, so if this is the first and this is the follow is end of file, and these two share nothing, so we're all set with S. Now we can move on to A, which has two paths. One in which it starts with just X because it's a terminal, and the other, I think you guys have epsilon in your first sets, and so these are disjoint. So we are good on that. Now we have to look at the follow sets, and we see that the follow of A is YWV. So things are looking good. These are not equal to each other. So A is all set. And then we have B, which is looking a little grosser. We look at path 1, which is that YBZ. And because it starts with a terminal, it's just Y. Then we have path 2, which is C, a little grosser because we have to know what the first of C is. So that's WV. There's no epsilon after it, so that path is over. And then we have the fourth one. Um, I'm just now yeah, okay. So the fourth one is this epsilon, or the third one, sorry. Okay, so that's looking fine. None of these have the same stuff in it. Then let's see if this is true. We look at the follow set of B and we have W, V, Z. So this is a problem. We have some overlap here. I guess I can change colors for that. We have some overlap. We have WV as overlap. And so, especially because we have this epsilon case, we don't know whether we're looking at the beginning of this path or whether we're looking at epsilon, in which, and I think that follow set case only really kicks in if there is an epsilon.
Yeah, you're correct. It's only if epsilon. You don't need to look at the false set if there is no epsilon in the non-terminal.
Okay, so this one was just me going off the rails, I guess. And so this is not a recursive descent, or this is not a valid recursive descent parser. There is technically a case where you can get around this. If you peak twice, sometimes you can get unique combinations, but that is not trivial. And I'm guessing the bounds of this question do not want you to do that, because it doesn't say like peak one or peak two.
Yeah, I
But
agree.
so just as an example of the alternative, let's say the follow set was just Z. And so let's look at how this predictive recursive descent parser would use. So we would have parse B, um, and then we would have T1, and this is going to be rough pseudocode peak one. We're just looking one ahead. And then we would do if T1 is equal to Y, then we can say um, we would just say, what is it? Let me look at the definition of B. Okay, so it would be something like expect or like get token. I would probably say it's expect Y, because that's the first terminal. And then we would call parse B again. And then we would call expect Z to go down that path. Else, and we look at the first of the second path, T1 equals W or V. Then we look at what that path entails, and it's just parse C. Technically, at this point, you can just do like a return because it has to be epsilon in the last case. But sometimes they will do something like the following, where they have a third case. I'm not the biggest fan of this, but so they do it a lot in the notes. Else if T1 equals Z, return else syntax error. And this is basically checking that the follow set matches. I don't really like it. I think there's a weird situation where it becomes necessary, but I don't like this because knowing the follow set is usually pretty difficult, but it's essentially equivalent, um, to just having a return at the end. Um, and the reason I kind of consider it redundant is because later on you're going to get to an expect that will check this, and if it's not Z, it'll fail that expect. So in my mind, it's not separating responsibilities, but that's how you would do it if it was a valid one. Um, did that answer your question, or do you want further clarification on some stuff? Okay, yeah, we can. Oh yeah, we okay. When we post the recording, we'll also post these slides, and then we will post. I guess I should clear the screen. In these slides at the bottom, like this is the exam modules 1 and 2. This is units. I think we posted the videos, the video, I guess. But we forgot to post the slides. So this will be in the slides we post for this one. After this presentation is over, it'll probably be less than an hour until I have the post up. Um, all right. Anything else for now? I guess everybody left. That's so sad.
That's so sad. I thought
We were
Gordon, I
too
thought
slow for them.
no, I swear that I honestly thought there'd be more people because it sounded like Gordon was actually gonna push it, but whatever.
Yeah, Gordon was like, I guess I should stop recording now. Does anybody have any other questions before I stop recording? I think we're good then. Oh,
Yeah.
sorry. Okay, we got one more.
All right. You want to do one? Yeah,
Um,
good.
that's a rough one. Okay. So if you remember what I said about the stack, um, so we have every time you declare a variable, you're making a box. So we will have this one, and it's going to have the name pp. This one will be QQ, and these are going to be global variables. The important thing to note about pointers when they're global, I don't know, Bozzy usually likes to ask this question. If a pointer is any value is global, it'll be initialized to a value of 0. But if it's local, like if pp and qq were inside of a function, we don't know what value it is because it's not zeroed out. 0 is null for most pointer implementations. And so global variables are initialized to null or global pointers. But like that AA, I guess I should have just waited until we did AA. So we see we have this AA. It looks more like a Q. And we have no idea what this is pointing to because it's a stack. Damn. Okay. Um, it's
Yeah,
a,
sorry. I was trying
it's all
to.
good.
I'm trying to give it
It
context
doesn't
for
show you
viewers.
typing, it just all appears at the end, which is
Oh,
interesting.
really? All right, sure.
Um, but because this is declared within the main function, it's up to just what was on the stack at the time. And because it's not initialized to null, this could be any random value. And so we consider that a wild pointer is what we usually call it. So if they ever ask you at this point, which are wild
Oh,
pointers, you look at what local variables haven't been set to a value. This is not the same as dangling references. Dangling references are manually freed. But we have B, and then we have C. And note, we're just creating a single box. Even though these are pointers, we haven't set them to anything, and a single variable declaration just asks for a single box. And so now we have that. And now we start mallocing. So malloc is also is box creation. So this is usually they'll be like, okay, this is M1, this is M2, this is M3, M4, M5, and M6. And that's not really as useful when we have names, but when we malloc something, we aren't giving it a name like we are with stack variables. So this will probably be like M7, or they'll tell you explicitly what to call it. And so we create a new box and point we say when we do equals, we're putting something inside of the target variable's circle. So here we're saying, hey, look at A's, or I guess this isn't AA. Look at A's box, go inside its circle, and set it to this pointer value. And so a pointer is always just represented as an arrow as opposed to an explicit value. Sometimes they'll want you, I didn't give myself enough space to put like M7 inside there, but I think that's distracting. Um, But the same thing happens here, where we have B. And notably, B, when we're mallocing, is pointing to an integer, while this is pointing, or we're here, the type of this would be int, and the type of this is an int double pointer. The reason this is cast to int triple pointer is because malloc always returns to a pointer to whatever it created. And so we do the same for C. This is M8, M9, and then we do the same for D. All right, now we have the dereference operator. And when we are talking about the dereference operator, we do the following steps. We look at the box. So we're talking about B's box right now. We go inside its circle and we follow the arrow. That's how we use the dereference operator. It's really simple with this one, but it's useful to have that step-by-step process when we're talking about larger ones, like we'll probably see with A. So we see dereference, we go to our circle, we follow the arrow. And so we're saying equals, again, wherever box we're at, equals says put the value inside the circle. So this becomes 10. Similarly, we're dereference C, follow the arrow, this becomes 20, and I guess I forgot to draw a circle. We look at D, go inside its box, follow what's inside the circle, this becomes 30. Now we have an inner scope. This is important to note because we said stack variables are automatically freed. Um, and so this temp after this point will be freed. That sometimes means if we have a pointer to temp and it's freed here, that's a dangling reference. So that's how you get a dangling reference when it refers to stack variables. And that's why you never want to return a pointer to something on the stack from a function. But regardless, for now, we're going to have this. I probably should change global or colors for the main, but we have temp. Again, we're just creating a single box. And then we're mallocing something. So this would be M11. This would be M12. And we're mallocing an int. And then we say, hey, go. We dereference. We start at the box, go to the circle, follow the arrow, set the value to 40. And then we dereference A. So we're dereferencing A. We go in this box, follow the circle. Now we're here. And we set it to the address of B. This is why I hate box circle diagrams, because now it's going to get ugly. So now we have this pointer to B's box. And remember, equals, we put something inside the circle. So we're putting an arrow to B inside of the circle for M7. It's getting a little ugly, so I would recommend, if you have the space and the time, redraw the entire box circle diagram whenever you start to erase stuff, because it's easy to lose track of things. And if I knew how to use Zoom better, I would be copying like my previous states before doing changes. Um, and so now we're setting B equals to C. So we're looking at B, we're going to its circle, and we're copying whatever's in C's circle. So let me get my eraser out. We kill that link. And now an arrow to M9 was in C's circle. So we just copy it over. Now this is what we call garbage memory, garbage memory, if I can spell. This is garbage because there is no way to access it. And if there's no way to access it, if and combining that with the need to manually free There's no way to access it. We need to manually free it. That means this cannot ever be freed again. And so this will just waste memory. It'll always be there. You can't ever give it back. Um, this is, yeah, this is an instance of garbage. And so now we're looking at C equals D. So now we're doing a very similar thing. We are looking inside both circles and we're copying whatever's in D's circle to C. There we go. And note that this is not garbage because we can access it using B. This can be called this dereference B name. And so the only one that's garbage is this one up here. And then we set D equal to dereference, double dereference A. And so we'll walk through how to do that. So what we do is, again, let's see if I'm, ooh, he's precise with it. So we're dereferencing A once. So we go inside the circle, follow the arrow. We're dereferencing A twice. We go inside the circle, we follow the arrow. Now we're at the box for B, basically. And we are setting that equal to D. Oh, I just got a Discord message. Hopefully it didn't record that. Um, and so we look at D. We are copying whatever is in our current box. So an arrow to M9. Ooh, this is gross. Okay. An arrow to M9, copying it into D. Still, of these three, this is the only one that's garbage because you can access this one using C. And here we are at point one. This is what your box circle diagram looks like. And at this point, I would recommend recreating this box circle diagram into a second section before you move on so you don't accidentally make a mistake and have to redo everything. Um, then we can look at point two. So now we are dereferencing B, precision erasure. Ooh, he's so clean with it. So now we are dereferencing B, which means we are looking at B, we're going inside the circle, following the arrow, and we're setting it equal to 100. So I'm going to set it equal to 100. And similarly with C, go inside the circle, follow the arrow. It's getting tedious when I say it, but the more you make this stuff step by step, the less you have to put on yourself to remember, which makes your consistency go up. Um, and then D, we go inside the circle, follow the arrow, and we change the value we just changed, which is interesting. And so this becomes 300. And then now we set, and this is why I really hate the box circle diagram. We set PP, go inside its circle, and we're setting it to an arrow to B's box. And then QQ is an arrow to D's box. Gross. Okay. Now we are at this point, and importantly, we've reached the end of the scope for temp. So now temp is gone. It's been ethered. But what temp is pointing to was malloc. That needs to be explicitly freed. This is now garbage memory. This is another common way that garbage memory happens is you malloc something and then you get rid of the pointer to it on accident. And so this is what it's looking like on point two. If I had to guess, the biggest mistake is that people forget this and they keep temp in play. Now we move on to the last section, and here, oh, gross. Is there any memory? Yeah, there's garbage. We're probably about to see dangling references. All right, so No! Okay, I thought I was being precise with it. All right. Uh, Precision. No! No! It's falling apart very quickly here.
Are you still recording this, by the way?
I am, yes.
Okay, good. I need to see. I need to remember this.
Precision. Okay. And now we are looking at free B. And what free does is it goes similar to dereference, goes inside the circle, follow the arrow, and kill whatever is here. And then similarly, we free C. So we look at C, go inside the circle, follow, and then we go, okay, this box is gone forever. And finally, we free A, we go inside the circle, follow the arrow, wherever, whatever box we're looking at, we yoink. Now, there's a few things to note at this point. I don't know how specific they get, but we have a few issues to answer that last question. One, this is garbage, and this is garbage. Those are two memory issues. We don't really have any wild pointers, but because everything has been set to something at this point. What we do have, although it doesn't affect anything, is right here. Notice that B, C, and D are pointing to boxes that have been culled, basically. This is the third memory issues. Dangling, I think dangling pointers are references. We're just going to call it dangling pointers, where we have a pointer to something that has been freed. This is a pretty big issue because when you free something, all it does is it like marks the memory free for use later by something else. It doesn't actually remove the memory or like clear it or zero it out. And so it's possible that for some time you keep using B and then randomly it crashes. Um, so you usually, when you free, you need to immediately set whatever you're freeing to null. Um, Otherwise, you open yourself up to a host of issues. If you accidentally free B again, you can double free memory, which can break some heap implementations. Um, and yeah, so we have two dangling pointers, three actually, because we have B, C, and D. Oh, and we also have A, so we have a fourth one. And yeah, so we have garbage and dangling pointers. And so those are your memory errors in this code. The dangling pointers, I don't know if they would really hone in on because you return without using any of them. Um, but yeah, they probably care more about the garbage. But the dangling pointers are still, oh, what did I do? All right. Is there any questions based on this? Or any more questions if you want to move on? Oh, we just had the other guy left. All right. So
Well,
no more questions. We're ready to head out. All right. Well,
yeah.
thank you for attending. Everyone else has left, but hopefully this was useful. I know this is not trivial. It's a lot. Um, and some of these concepts sometimes take some time sitting with, but hopefully good luck on your exam. And I guess I'll end the recording there.